In number theory and combinatorics, a partition of a positive integer n, also called an integer partition, is a way of writing n as a sum of positive integers. Two sums that differ only in the order of their summands are considered the same partition. For example, 4 can be partitioned in 5 distinct ways. 4 3 plus 1 2 plus 2 2 plus 1 plus 1 1 plus 1 plus 1 plus 1. The order-dependent composition 1 plus 3 is the same partition as 3 plus 1, while the two distinct compositions 1 plus 2 plus 1 and 1 plus 1 plus 2 represent the same partition 2 plus 1 plus 1. A summand in a partition is also called a part. The number of partitions of n is given by the partition function p, so p equals 5. The notation lambda n means that lambda is a partition of n. Partitions can be graphically visualized with Young diagrams or Ferrer's diagrams. They occur in a number of branches of mathematics and physics, including the study of symmetric polynomials, the symmetric group and in-group representation theory in general. Examples: the 7 partitions of 5 are 5 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1. In some sources, partitions are treated as the sequence of summands, rather than as an expression with plus signs. For example, the partition 2 plus 2 plus 1 might instead be written as the tuple, or in the even more compact form where the superscript indicates the number of repetitions of a term. Representations of partitions. There are two common diagrammatic methods to represent partitions: as Ferrer's diagrams, named after Norman MacLeod Ferrers, and as Young diagrams, named after the British mathematician Alfred Young. Both have several possible conventions. Here, we use English notation, with diagrams aligned in the upper left corner. Ferrer's diagram: the partition 6 plus 4 plus 3 plus 1 of the positive number 14 can be represented by the following diagram. The 14 circles are lined up in 4 rows, each having the size of a part of the partition. The diagrams for the 5 partitions of the number 4 are listed below. Young diagram: an alternative visual representation of an integer partition is its Young diagram. Rather than representing a partition with dots, as in the Ferrer's diagram, the Young diagram uses boxes or squares. Thus, the Young diagram for the partition 5 plus 4 plus 1 is, while the Ferrer's diagram for the same partition is. While this seemingly trivial variation doesn't appear worthy of separate mention, Young diagrams turn out to be extremely useful in the study of symmetric functions and group representation theory. In particular, filling the boxes of Young diagrams with numbers obeying various rules leads to a family of objects called Young tableaus, and these tableaus have combinatorial and representation theoretic significance. As a type of shape made by adjacent squares joined together, Young diagrams are a special kind of polyomino partition function. In number theory, the partition function p represents the number of possible partitions of a natural number n, which is to say the number of distinct ways of representing n as a sum of natural numbers. By convention, p equals 1, p equals 0 for n negative. The first few values of the partition function are equals 1, 1, 1, 2, 3, 5, 7, 11, 15, 22, 30, 42, 56, 77, 101, 135, 176, 231, 297, 385, 490, 627, 792, 1002, 1255, 1575, 1958, 2436, 3010, 3718, 4565, 5604. The exact value of p has been computed for large values of n. For example, p equals 190,569,292. P is 2406146786403262247392149727991, or approximately 2.406115 times 1031. And P is 36,167,251,325, 906,916,435,144, or approximately 3.61673 times 10,106. As of June 2013. Update. The largest known prime number that counts a number of partitions is P, with 12,198 decimal digits. Generating function. The generating function for P is given by expanding each factor on the right-hand side as a geometric series. We can rewrite it as the xn term in this product counts the number of ways to write n equals a1 plus 2a2 plus 3a3 plus equals plus, where each number I appears I times. This is precisely the definition of a partition of n, so our product is the desired generating function. More generally, the generating function for the partitions of n into numbers from a set A can be found by taking only those terms in the product where k is an element of A. This result is due to Euler. The formulation of Euler's generating function is a special case of a Pochhammer symbol and is similar to the product formulation of many modular forms, and specifically the Dedekind data function. The denominator of the product is Euler's function and can be written, by the pentagonal number theorem, as where the exponents of x on the right-hand side are the generalized pentagonal numbers, i.e., numbers of the form half a meter, where m is an integer. The signs in the summation alternators. This theorem can be used to derive a recurrence for the partition function. P equals P plus P minus P minus P plus P plus P minus P minus, where P is taken to equal 1, and P is taken to be 0 for negative k. Congruences. Srinivasa Ramanujan is credited with discovering that congruences in the number of partitions exist for arguments that are integers, ending in 4 and 9. For instance, the number of partitions for the integer 4 is 5. For the integer 9, the number of partitions is 30. For 14 there are 135 partitions. This is implied by an identity, also by Ramanujan, where the series is defined as he also discovered congruences related to 7 and 11. And for P equals 7 proved the identity since 5, 7, and 11 are consecutive primes. One might think that there would be such a congruence for the next prime 13, for some A. This is, however, false. It can also be shown that there is no congruence of the form for any prime B other than 5, 7, or 11. In the 1960s, O.L. Atkin of the University of Illinois at Chicago discovered additional congruences for small prime moduli. For example, Ono proved that there are such congruences for every prime modulus. Later, Algren and Ono showed there are partition congruences modulo every integer coprime to 6. Partition function formulas. Recurrence formula. Leonhard-Euler's pentagonal number theorem implies the identity where the numbers chapter 1, 2, 5, 7, that appear on the right side of the equation are the generalized pentagonal numbers for non-zero integers k. More formally, where the summation is over all non-zero integers k and p is taken to be 0 if m less than 0. Approximation formulas. Approximation formulas exist that are faster to calculate than the exact formula given above. An asymptotic expression for P is given by this asymptotic formula was first obtained by G. H. Hardy and Ramanujan in 1918 and independently by J. V. Uspensky in 1920. Considering P, the asymptotic formula gives about 2.4402 times 1031, reasonably close to the exact answer given above. Hardy and Ramanujan obtained an asymptotic expansion with this approximation as the first term. where here, the notation equals 1 implies that the sum should occur only over the values of m that are relatively prime to n. The function s is a Dedekind sum. The error after v terms is of the order of the next term, and v may be taken to be of the order of. As an example, Hardy and Ramanujan showed that p is the nearest integer to the sum of the first v equals 5 terms of the series. In 1937, Hans Rademacher was able to improve on Hardy and Ramanujan's results by providing a convergent series expression for p. It is the proof of Rademacher's formula involves Ford circles, Fairy sequences, modular symmetry and the Dedekind data function in a central way. It may be shown that the kth term of Rademacher's series is of the order so that the first term gives the Hardy-Ramanujan asymptotic approximation. Paul Erdos published an elementary proof of the asymptotic formula for p in 1942. Techniques for implementing the Hardy-Ramanujan-Rademacher formula efficiently on a computer are discussed in Johansson, where it is shown that p can be computed in softly optimal time O. The largest value of the partition function computed exactly as p, which has slightly more than 11 billion digits. Restricted partitions. In both combinatorics and number theory, families of partitions subject to various restrictions are often studied. This section surveys a few such restrictions. Conjugate and self-conjugate partitions. If we now flip the diagram of the partition 6 plus 4 plus 3 plus 1 along its main diagonal, we obtain another partition of 14. By turning the rows into columns, we obtain the partition 4 plus 3 plus 3 plus 2 plus 1 plus 1 of the number 14. Such partitions are said to be conjugate of one another. In the case of the number 4, partitions 4 and 1 plus 1 plus 1 plus 1 are conjugate pairs, and partitions 3 plus 1 and 2 plus 1 plus 1 are conjugate of each other. Of particular interest is the partition 2 plus 2, which has itself as conjugate. Such a partition is said to be self-conjugate. Claim. The number of self-conjugate partitions is the same as the number of partitions with distinct odd parts. Proof. The crucial observation is that every odd part can be folded in the middle to form a self-conjugate diagram. One can then obtain a bijection between the set of partitions with distinct odd parts and the set of self-conjugate partitions, as illustrated by the following example. Odd parts and distinct parts. Among the 22 partitions of the number 8, there are 6 that contain only odd parts. 7 plus 1, 5 plus 3, 5 plus 1 plus 1 plus 1, 3 plus 3 plus 1 plus 1, 3 plus 1 plus 1 plus 1 plus 1 plus 1, 1 plus 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 1. Alternatively, we could count partitions in which no number occurs more than once. If we count the partitions of 8 with distinct parts, we also obtain 6. 8, 7 plus 1, 6 plus 2, 5 plus 3, 5 plus 2 plus 1, 4 plus 3 plus 1. For all positive numbers, the number of partitions with odd parts equals the number of partitions with distinct parts. This result was proved by Leonhard Euler in 1748 and is a special case of Glazer's theorem. For every type of restricted partition, there is a corresponding function for the number of partitions satisfying the given restriction. An important example is Q, the number of partitions of n into distinct parts. The first few values of Q are equals 1, 1, 1, 1, 2, 2, 3, 4, 5, 6, 8, 10. The generating function for Q is given by the second product can be written, whereas Euler's function, the pentagonal number theorem, can be applied to this as well, giving a recurrence for Q. Q equals AC plus Q minus Q minus Q plus Q plus Q minus Q minus, where AC is m if k equals 3 square meters minus m for some integer m and is 0 otherwise. restricted part size or number of parts using the same conjugation trick as above. One may show that the number pk of partitions of n into exactly k parts is equal to the number of partitions of n in which the largest part has size k. The function pk satisfies the recurrence pk equals pk plus pk minus 1 with initial values p0 equals 1 and pk equals 0 if n0 or k0. One possible generating function for such partitions, taking k fixed and n variable, is more generally, if T is a set of positive integers, then the number of partitions of n, all of whose parts belong to T, has generating function. This can be used to solve change-making problems. As two particular cases. One has that the number of partitions of n in which all parts are 1 or 2 is, and the number of partitions of n in which all parts are 1, 2 or 3 is the nearest integer to 2/12. Asymptotics. The asymptotic expression for P implies that where, if A is a set of natural numbers, we let par denote the number of partitions of n into elements of A. If A possesses positive natural density alpha, then, and conversely, if this asymptotic property holds for par, then A has natural density alpha. This result was stated, with a sketch of proof, by Erdos in 1942. If A is a finite set, this analysis does not apply. If A has k elements whose greatest common divisor is 1, then partitions in a rectangle and Gaussian binomial coefficients 1 may also simultaneously limit the number and size of the parts. Let P denote the number of partitions of n with at most m parts, each of size at most n. Equivalently, these are the partitions whose Young diagram fits inside an m times on rectangle. There is a recurrence relation obtained by observing that counts the partitions of n into exactly m parts of size at most n, and subtracting 1 from each part of such a partitions yields a partition of n minus m into at most m parts. The Gaussian binomial coefficient is defined as the Gaussian binomial coefficient is related to the generating function of P by the equality rank and phi square. The rank of a partition is the largest number k such that the partition contains at least k parts of size larger than k. For example, the partition 4 plus 3 plus 3 plus 2 plus 1 plus 1 has rank 3 because it contains 3 parts that are 3, but does not contain 4 parts that are 4. In the Ferrers diagram or Young diagram of a partition of rank R, the R times R square of entries in the upper left is known as the phi square. The phi square has applications within combinatorics in the proofs of various partition identities. It also has some practical significance in the form of the H-index, Young's lattice. There is a natural partial order on partitions given by inclusion of Young diagrams. This partially ordered set is known as Young's lattice. The lattice was originally defined in the context of representation theory, where it is used to describe the irreducible representations of symmetric groups Sn for all n, together with their branching properties. In characteristic 0, it also has received significant study for its purely combinatorial properties. Notably, it is the motivating example of a differential posit algorithm. The partition function is inherently recursive in nature since the results of smaller numbers appear as components in the result of a larger number. For example, this set of partitions of 7, 6 plus 1, 5 plus 1 plus 1, 5 plus 2, 4 plus 1 plus 1 plus 1, 4 plus 2 plus 1, 4 plus 3, 3 plus 1 plus 1 plus 1 plus 1, 3 plus 2 plus 1 plus 1, 3 plus 2 plus 2, 3 plus 3 plus 1, 2 plus 1 plus 1 plus 1 plus 1 plus 1, 2 plus 2 plus 1 plus 1 plus 1, 2 plus 2 plus 2 plus 1, 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, can be arranged by grouping the largest summand as follows: 7, 6, 1, 5, 1 plus 1, 2, 4, 1 plus 1 plus 1, 2 plus 1, 3, 3 1 plus 1 plus 1 plus 1 2 plus 1 plus 1 2 plus 2 3 plus 1 2 1 plus 1 plus 1 plus 1 plus 1 2 plus 1 plus 1 plus 1 2 plus 2 plus 1 1 1 plus 1 plus 1 plus 1 plus 1 plus 1. Let P be the number of partitions of n using only positive integers less than equals m. Clearly P equals P, and if m greater than n, then P equals P equals P. Then, to compute P, the above list leads to the following, where the indented list items represent the count of the number of items in that grouping. 7p, 6p, 5p, 4p, 3p, 2p, 1p. This arrangement illustrates the recursive nature of this function. Given the above as intuition, here is a Java program which computes P, counts the number of ways of representing n as a distinct sum of positive integers less than equals m. Get param n number to sum to get param m restriction on the component numbers get return number of ways public static long key if recursive stopping condition return 1 if using component numbers greater than n doesn't contribute any more ways to sum to n return p long sum equals 0 4 sum equals sum plus p return sum counts the number of ways of representing n as a distinct sum of positive integers. Get param n number to sum to get return number of ways public static long key return p. This algorithm is suitable for n less than equals 50 or so, but since it recomputes smaller values over and over, it is not time efficient for larger values. This benefits greatly from memoization. Here is the same algorithm with memoization implemented. Note that this now returns a big integer to allow it to compute the value of something like p. Package partition function, import java.math.biginteger, import java, util, hash map, import java, util, map, public class partition function, static final, private map less than string. Big integer greater than cache equals new hash map less than greater than, if recursive stopping condition return big integer 1, if using component numbers greater than n doesn't contribute any more ways to sum to n return p string cache key equals n plus m big integer sum equals cache.get if return sum equals big integer 0 4 sum equals sum.add cache.put return sum counts the number of ways of representing n as a distinct sum of positive integers.